Hi folks, we're going to take a look at the solution to number 19 on page 570. So here's the question. So we have a railroad bridge and we have a river that are at right angles to each other, and the bridge is 20 meters above the river. So you have to think that you've got the road up on top and then you've got the river at right angles but separated. So you can see that separated by 20 meters. Okay. Then they give us information about how quickly the boat and the train is traveling, and they're asking us how fast the two are separating after 10 seconds. Okay. Now, what makes this problem significantly more difficult is the fact that we have to try to draw a 3D diagram. Okay, so similar to those trigonometry problems that you'd have solved in grade 11 as opposed to grade 10, one of the complexities that came into play were these 3D diagrams. Okay, so we're going to do our best to draw a picture to represent this. So let's say this represents where the train is coming. Okay, and I'm going to try to draw sort of a 3D. Okay, so here, if that represents the river, and this is the height above the river, which is 20 meters. Okay, you have to think that here we've got a right angle. Okay, so let's see what's going on. So we want to represent a general distance between a person on the train and a person on a boat. So what they're telling us is that at a particular moment when the train is at the center of the bridge, the boat passes exactly at that point. So when we try to draw the distance that is traveled by both, I'm going to start the train from this center point, and then I'm going to start the boat again from that point just below the bridge. Okay, so these two arrows here represent how far the train has traveled, how far the boat has traveled, and what we want to do is we need to determine how quickly these two are moving away from each other, so the actual distance between a person on the train and a person on the boat. So that's what we're trying to determine, is the rate of change of this distance with respect to time. Okay, so let's give some names to things. So let's say we have the train moves a distance of x, and the boat moves a distance of y, and I have to somehow relate these two, because these are the rates of change that I know, to this distance here. Okay, and I think what I'm going to do is I'm going to start by drawing a right angle triangle here. Again, you got to think this is 3D, right angle from there. Okay, so that I can incorporate this distance y with that triangle here. Okay, which is going to incorporate the distance of the train, the distance we're looking for, okay, and this is connected to the distance traveled by the boat. Okay, so this is just going to be given by Pythagoras, since it's just the hypotenuse of that triangle. So this is just going to be the square root of y squared. Okay, now this is where we have to make a bit of a choice. So if you go back and look at the question, we see that the bridge is given, the height of the bridge is given in terms of meters, but the rates of change are given in terms of kilometers per hour. Okay, and since the goal is to determine how fast they're moving, I think we're going to want to work in kilometers per hour. So I'm going to rewrite this in terms of kilometers. So 20 meters divided by 1,000 is 0.02 kilometers. Okay, so makes more sense. Since I want my final answer in kilometers per hour, I should get everything in terms of kilometers. Okay, so now we have to look at this triangle here, but I want you to notice that this sort of plane here, if you think of it as a plane, is perpendicular to this one here. So you actually have another right angle triangle here. Okay, so what's nice is that I can again use Pythagoras. So I can write a formula for d, okay, and I'll use the unsquare rooted version as x squared, which is one leg, plus this side squared, but since there's a square root, it's just going to get rid of the square root. So we just have plus y squared plus 0.02 squared. Okay, I'd actually like you to keep this in the back of your heads, because this idea of finding this type of relationship will come back when we're at a particular point in vectors. Okay, so what we have is we have a relationship for this distance d, but it's given in terms of two variables. Now that's not a problem because they give me the rate of change of both of these variables. Okay, so I don't need to try to write x in terms of y or y in terms of x because I have both those pieces of information. Okay, so now I'm going to take the derivative of both sides. Remember, we're differentiating with respect to t. Okay, so here we have 2d d prime equals, this is going to be 2x x prime plus 2y y prime plus the derivative of a constant is just going to be 0. Okay, so divide 2 from both sides of the equation, so it makes it a little simpler there. And here, what do we have? We've got d prime then, which is that thing we're looking for. So we have x times x prime. So here it says determine the rate of change after 10 seconds. So this is where, again, this is why it's in section C here, because there's a bunch of little complexities. Okay, we got to figure that the train is moving at 60 kilometers per hour. So we have to write this in seconds. So 60 kilometers in 1 hour. Well, let's find how far it travels in 1 second. So 3,600 seconds in an hour. Okay, but it's after 10 seconds, so I'll take that number, multiply by 10. Okay, so that means the distance traveled is going to be 0.17. Okay, now the speed at which the train is traveling, we know is 60 kilometers an hour. Okay, plus, now something similar for the distance traveled by the boat in 10 seconds. So again, 20 kilometers an hour. So I divide by 3,600 to find how many kilometers in 1 second. And since it's after 10 seconds, multiply by 10. So this is 0.056. Okay, and the boat is traveling at 20 kilometers an hour. Okay, and then of course I have to divide by this d value. Okay, so let's determine that d value. So I essentially need to use this equation, but now I know I'm calculating the d value after 10 seconds. Sorry, I'm going to have to put up with this shadow here. Okay, so let's calculate that here. So we have d is just going to be equal to the square root. Okay, since I need d, I'm going to actually take the square root. So again, after 10 seconds, x is equal to 0.17, so it'll be 0.17 squared plus, after 10 seconds, we calculated y was 0.056, 0.056 squared, plus, and the 0.02 squared. Okay, so let's just calculate that quickly here. So we've got square root of 0.17 squared plus 0.056 squared plus 0.02 squared. Okay, and that gives me 0.18. Okay. So now, let's just incorporate that into this here. So we've got 0.17 times 60 plus 0.056 times 20 equals, okay, and divided by, what did we find again? It was 0.18 divided by 0.18, and here we get 62.9. Okay, now remember, because we kept everything in terms of kilometers, we know that this is just going to be kilometers per hour. Okay, so despite the fact that the actual solution is quite short, there was a lot of stuff going on here. So number one was to recognize that we were dealing with a 3D problem, but it just turned out to be a series of right-angle triangles that we could work with. Okay, so just subsequent, couple of uses of Pythagoras. The other thing that was important to deal with were the units. Okay, so I made the choice to just turn everything in terms of kilometers. Since they were asking me for a speed, made sense to keep the speed in the same units. So notice I kept everything in kilometers. And because the time value given was in seconds, again, I had to do a bit of change of units. Okay, so that's it for this one.